Cool. So this picture should come very familiar to all of you, which is the general structure of large-scale analytics. So at the very top, we have compute workers that will operate on local shards of data independently, and usually this doesn't involve communication. And then we have an optional combined phase where data could potentially be deduplicated and combined before eventually going on to the shuffle phase, where we may end up resharding the data and generating a lot of communication. So why is shuffle interesting as a component to look at? In fact, there is a lot of work that has been done in this area over the last decade and even longer. The first thing is that it involves a combination of CPU, bandwidth, and latency. And so there's resources required to do compression, serialization, message processing, and transmission. And what we found is that there's really no one-size-fits-all solution, right? So if you look at different kinds of workloads, such as DBMS, MapReduce, graph processing, they all involve different trade-offs and different ways of tuning the shuffle performance. And also more interestingly, there is an emergence of new cloud platforms, serverless, and more recently, disaggregated memory and storage. So disaggregated storage has been around for a while, but now increasingly for the purpose of elastic scaling, we're also seeing more and more proposals for disaggregated memory, where you could access elastic memory through high-speed networks like RDMA. Now, as a result, we see that looking forward, there'll be more and more challenges in optimizing shuffle. And part of the reason behind the challenge is it's very workload dependent. Some shuffle requires going to the disk, some require combining, aggregating, and others involve doing data redundant deduplication. And also there is dependency on data center architecture, which would involve CPU, network, and communication among different machines. But more importantly, a lot of this must also adapt to changes, right? There could be failures in the data centers, which would result in topology updates. There's disaggregated compute, memory, and storage. And we see that increasingly data center designs are becoming more complicated as well, right? There's more and more emerging hardware, smart NICs, and so on. So our proposal here is to come up with a general framework, which we call TeShu, which stands for templated shuffle layer. And here's our kind of initial design and vision behind it. And the idea is that TeShu should adapt to workload and data center infrastructure changes. And we want to be able to support existing data analytics systems and also make it future-proof, right? So we could enable new ones. And what users will provide in this case are shuffle primitives that we call templates, and with unknown characteristics of workloads and infrastructures that you can supply as parameters. And what data analytics systems will do is then instantiate these templates by populating the parameters. And here's a picture that illustrates what it looks like. Now, in the rest of the talk, I'm going to provide an overview of the TeShu design, talk a little bit about expressiveness, some of our preliminary evaluation results, and also future directions. Now, so here's the architecture. So there is a shuffle manager in TeShu, and it's deployed as a service. And it stores a number of these shuffle templates and coordinates the shuffle invocations. Now, during job execution, the application will invoke the shuffle API, typically using some form of RPC request in order to get these templates. And then this will then be instantiated into shuffle plans. Now, while this is executing, there's runtime sampling and measurements that happens in the background. And basically that allow us to then determine at runtime how to optimize the shuffling, right? And to adapt to any sort of changes that's needed at runtime. All right, so what are the number of primitives for the shuffle template? So we kind of designed this as a Python-like program with a number of primitives: send, receive, fetch, partition, combine, and sampling. And the first three are really like basic communication, supporting both push and pull. And we populate it using framework native communication libraries. Now, the next three are what we would typically associate with any kind of shuffle service, which involves partitioning, combining, and sampling. And in this case, this will be populated or given as input using the shuffle arguments, and also tuned based on our runtime sampling approach. Now, here's a really simple example of how one would be able, for example, to implement a pool-based vanilla shuffling, where on the sender side, you would partition the data into buffers based on the partition function. And then on the receiver side, you would fetch from these buffers. All right, so I'm going to next talk about the Shuffle API. And basically, it is viewed in terms of instances of concurrent communication between a fixed set of sources and destinations. So there is arguments that allow you to input the IDs of the worker, the template, and the shuffle call. There's also source and destination lists and also data buffers. And last but not least, user-defined functions for partitioning and combining. And in combination, this could then be used to instantiate what the shuffle is going to look like. And the partition function basically is a way for you to map a piece of data to a destination worker. And the combine function allows you to merge two pieces of data into one. Now, in terms of shuffle management, we would invoke the shuffle manager and the application. And basically, this would involve implementing shuffle templates that are stored in the shuffle manager. So the user will select the shuffle template and request the template, instantiate, and then start executing it. And in fact, you can even cache these templates so you don't have to go back to the shuffle manager every time. And at runtime, carry out different kinds of measurements that can allow you to tune the shuffle performance. Now, at the same time, we also kind of track what are the shuffles that have been issued and completed. And this could be a way for you to do fault-tolerant management and so on. All right, I'm going to next talk a bit about the expressiveness. So we have taken this templating approach and looked through the existing literature and try to implement a number of proposed shuffle mechanism that has been proposed in the past. Our intent isn't really so much to kind of reinvent new shuffles, but rather to see if we could cover a widespread of different shuffle algorithms that has been proposed. And here are a number that we have looked at. And one of the main takeaways is that they are all quite different. So for example, one of the approach would use a ring approach. The other one uses a two-level exchange, and they all have different patterns of communication. Now, another interesting thing that we looked at was, could we actually implement infrastructure-aware shuffling using our approach? And one of the things to note is that in the data center, you could actually have many opportunities to do on-the-fly deduplication and combining that's infrastructure aware. So for example, you could do combination at the server level, at the rack level, at the cluster level, or at the global level as well. And interestingly, we found that there are trade-offs, right? So you can always do combination at every single level, but in a lot of times they generate a lot of overhead. And suppose if your network is not oversubscribed, right? So you have sufficient bandwidth, then the additional compute resources that you put into to do this different levels of combining may actually backfire. Now, this is where the sampling approach of TeShu comes into play, where you could actually sample the data distribution at runtime and then make informed decisions on whether to do this combination. And in fact, in our paper, you can look at this adaptive shuffling template, and it could be written in a couple of lines of code. All right, very quickly, I'm sort of running out of time. It turns out data sampling itself is also a tricky problem that you need to look at, because if you do random sampling, you may not get very good data. And on top of that, incur high overhead. So in our paper, we come up with what we call a partition-aware sampling, where in a nutshell, what we do is we look at all the possible destination spaces, and then we hash them into different buckets. And rather than do a sweep over all the different sets of data, we will select one or maybe two of these buckets and then do the sampling within that bucket. Now, in terms of evaluation, we have implemented TeShu and run it on a cluster of machines on 10 servers with 16 cores. And we emulate different levels of oversubscription, right? So where oversubscription is the ratio between the inter-rack communication, which is more global, versus the intra-rack, right? So if you have 10:1, that means there's a lot more demands on the higher level switches in terms of bandwidth versus 1:1 on the other extreme, which means the network is relatively underutilized. So we focus on graph analytics because it's a challenging workload, and we look at page rank and single source shortest paths and evaluate it on 2 types of data sets. So in terms of evaluation results, so here are some of the main takeaways. The first is that if you do things in a partition-aware manner, you can get very high accuracy. In fact, when we compare to what the ground truth is in terms of the deduplication level, we can get really close even if we don't have a high sampling rate. On the other hand, if you do random sampling, the results can get bad really quickly. And this graph here shows the trade-offs in partition-aware sampling, where basically, if you sample a lot, it causes high overhead and high variance in your performance. But if you're willing to sacrifice a little bit of accuracy, you see that the sampling performance drops drastically. All right, so I have 1 more minute, so I'll try to wrap this up really quickly. This slide basically provides some additional evaluation results. And main takeaway is that we get up to 14x performance improvement. And in fact, for different subscription ratios, the adaptive algorithm can choose to do shuffling in a different way, right? Kind of validating the approach. All right, in the last minute, I just want to take a kind of look into the future, right? So we view TeShu as kind of our first attempt at seeing, could we actually build shuffle in a generalized manner? I think we feel confident. The answer is yes, but there's a lot of interesting work to be done moving forward. So for example, instead of optimizing a single shuffle, could we optimize multiple shuffles at the same time? How do we deal with failures and stragglers in more generalized manner? There's a lot of interesting work on new smart NIC designs. So could we combine that together with in-network processing to further improve performance? And with emerging hardware in disaggregation, we would love to see how this approach could apply to future data centers. All right, so with that, I think I ran out of time. Just put the summary slide here and happy to take any questions.